Yeah, so in the last video we learned that there are many different CNN architectures out there. In this video, let's highlight some of them and look at their key features. So in the previous video we introduced this figure which plots the predictive accuracy, the size and the computational performance of the different architectures. So while this figure is from 2016, it still highlights most of the important architectures, and many of the ideas used in these architectures are still very influential for designing new architectures. So there is of course AlexNet, which some people call the birthday of deep learning. And AlexNet, as we have learned in the previous video, it was very famous because it won the ImageNet 2012 competition. And the other reason why it's famous is that it demonstrated that we can use GPUs for the efficient training of neural networks on large datasets. Another very popular architecture is the VGG16 architecture. So this is a network consisting of 16 layers, and it's essentially very similar to AlexNet, except that it is a bit larger and has a higher predictive accuracy. Another popular architecture is GoogleNet, or also called Inception. So GoogleNet is based on the so-called Inception modules. And Inception modules in turn are based on multiple convolutional layers in parallel, where these convolutional layers have smaller kernel sizes than usual. And that is to design different types of feature extractors and also to keep the number of parameters small compared to using, let's say, convolutional layers with large kernels. So the key idea behind these Inception modules is that we can keep the model smaller by using these smaller kernel sizes, and we can also then extract features of various scales by having these different kernel sizes. So another interesting aspect about the Inception or GoogleNet architecture is the loss function. So in typical networks we have this last output layer where we attach the loss function. However, in Inception we also have these so-called auxiliary output layers with additional loss function. And the total loss function is essentially a sum over all these different losses. So why do we use these auxiliary losses in Inception? So the idea here is that it is sometimes hard to train very large neural networks. So due to backpropagation and how it works, the signal sometimes degrades when we have a very large network and we go from this output layer to the far away input layer. By having these auxiliary losses, we can ensure that each small subpart of the network learns well, which then helps with the overall training of the neural network. And the maybe most popular architecture on this plot here is the Resnet architecture. Resnet stands for Residual Neural Network. Here we have actually three types of ResNets: Resnet 34, Resnet 50, and Resnet 101. So the number here refers to the number of layers. And you can see 101 is actually a very large number of layers. So how does Resnet actually train well if we have such a large number of layers? So one way would be using these auxiliary losses that we just learned about in the Inception architecture, but Resnet actually uses a different type of trick. So the key idea behind residual networks is that we have these so-called skip connections, which are essentially identity functions. So a skip connection is essentially giving the network the possibility to skip entire layers. So why are these skip connections useful? So assume some of these layers are bad just by chance. Having a skip connection can allow us to skip these bad layers without really harming the overall performance of the network. Now note that there are many additional architectures that have been created in the recent years, but most of these architectures are still based on these key ideas that we introduced in this video. So if you are interested, I will share more of these recent architectures in the resource section below. There's one more architecture though that I want to highlight before we end this video though. So this architecture is a convolutional vision transformer hybrid. So transformers have been becoming popular recently, as you may have heard, and we will in fact cover transformers in the upcoming unit when we talk about natural language processing. However, transformers can also be used for vision tasks, and in particular they are very useful when they are combined with convolutional layers. So in this convolutional vision transformer hybrid, we use a CNN part or convolutional layers as the patch extractors. And then the extracted patches are passed to this transformer encoder, which will produce encodings that are then passed to multilayer perceptron layers, which then do the classification. But yeah, if you have not heard about transformers yet, don't worry, we will discuss transformers in Unit 8. Alright, we talked a lot about CNNs and we saw a lot of different types of architectures. I think it's about time that we now finally train CNNs ourselves. So stay tuned for the next video.